Hi, this single video is designed to introduce the OpenRAN or ORAN, especially for the peoples who have just decided to deep dive into the OpenRAN world, but they do not know that how to start and where to start. This single video going to be enough to develop that foundation. This video will cover the general architecture of OpenRAN, their deployment strategies, cloudification, RAN intelligent controllers applications, AI and machine learning concept to the gateway of OpenRAN, etc. So let's start. In this series, we would be covering Open Radio Access Networks from basics and gradually increase the level. Hence, if you are familiar with some topics, you can join from the label which is best fit for you. In this series, we would be starting from the origin of OpenRAN. Then we will understand what is OpenRAN. Then we will have some basic understanding on OpenRAN terminologies. Later, we will go through to the OpenRAN standards. We will understand the OpenRAN design goals. We will understand the objectives behind the continuous evolutions in the OpenRAN. Implementation on OpenRAN. Implementation of OpenRAN is not super easy. There are some challenges to implement ORAN in the real world. We will also talk about those challenges too. Okay, so let's start. In this session, we will have some brief about the origin of OpenRAN. We will know what is OpenRAN and what are the common terminologies of OpenRAN. So, what is the origin of OpenRAN? Well, there is a community named as Telecom Infra Project. In short, we call that TIP, which is led by the Facebook or Meta. There are many big giant companies and vendors from the domain of telecom, operators, hardware suppliers, service providers, and also IT industry came together with a vision to innovate the radio access networks and overcome the biggest challenge of hardware and software dependency. They are collaborating to produce new products and solutions which can have the flexibility of interoperable. So, Telecom Infra Project (TIP) is a group of companies and organizations working to develop the generalized solutions and have a vision to develop the advanced global connectivity. OpenRAN will provide the multi-vendor acceptance of the product and services and will allow the flexibility to choose from the wider scope of possibilities. And with the continuous development and innovations, they plan to offer new services to any operator worldwide. There are more big communities who are also working towards evolving the overall ecosystem of OpenRAN, like ORAN alliances form. However, these are theoretical knowledge, but do not skip this important information because it is really important to know for deciding a good career on any specific domain. It is super important to know that what companies and organizations are working in the field and actively participating in the development and implementation of technology. Anyway, let's talk about what is ORAN, Open Radio Access Network, all about. So the highly focused word is open. Open means here that anything is not a property of any individual, company or organization. It can be anything, like it can be a hardware, it can be a software, it can be an interface, or it can be an API, source code, etc. This means operators will no longer bound to use a specific product from the provider. Because with OpenRAN, operator will have the flexibility to choose hardware from one supplier, then they can choose software from another provider, API or source code from someone else, he can choose the interface, etc. Means this will allow operator or telcos to have more customization and flexibility to choose. This is a shift from proprietary to COTS. COTS means commercial off the shelf. So from the RAN perspective, whatever the parts and components are present for radio access network like hardware or software or the interface, etc., operators are bound to use all these things from a specific vendor or provider in the traditional RAN systems. And because of that, they have very specific ecosystem and they cannot go beyond that limitation. Means they may or may not have the trending features which other vendors are supporting. But as an operator, you cannot use that until your existing provider starts supporting that feature. And that is the big reason why big organizations and giants came together for an effective solution and can be a win-win for all without any such dependency. So with OpenRAN, the idea is to innovate the overall ecosystem of radio access networks and to shift from the proprietary ecosystem to a non-proprietary ecosystems. With this new non-proprietary ecosystem, operators can procure the hardware from one supplier or vendor, can choose the best fit software based on the budget, needs, etc. and can also choose for the user interface, UI, UX, etc. There would be no dependency on single provider. In that case, isn't it great news for operator? Of course, yes. The second important building block of Open RAN is software. There are few more communities like ONAP. This is with the collaboration by ORAN alliances. This community has the major focus on evolving the software functions. The vision is to come up with new and trending features. The goal is also to overcome the problems and issues in the current Open RAN ecosystems by debugging them and solving them. Another important factor of Open RAN is cloud or cloudification. This is equally important because in the traditional RAN systems, the resource utilization are very unbalanced. In some areas, they are underutilized, and in some other areas, they are overutilized. Hence, the user experience is not consistent. So this is expected that this highly unbalanced situation with the current RAN system can be improved with Open RAN ecosystem. And the overall efficiency of the system can be increased and end users can experience the better and more consistent services. Another interesting factor which can push Open RAN to new heights is acceptance of third-party applications and features, which also include the highly trending technology of AI, artificial intelligence and machine learning. How? We will talk about that little later, but definitely with the help of these trending technology, the efficiency of the overall system will definitely improve to new heights, which has not been achieved with the current RAN ecosystems yet. Also, there is a shift of disaggregated RAN, where the different functionalities are being disaggregated in Open RAN. So some of the functionalities would be closer to the user, and you can say closer to cell and site, which are real-time sensitive features, and other functions which are non-real-time sensitive can be taken away from the cell and site, like maybe at higher level or maybe at regional level. They can be operated from backend where latency do not affect the services much. In traditional ecosystem, this you can relate like some decisions BTS or eNodeB or gNodeB takes by itself, which need to be handled quick. And for some decisions, eNodeB or gNodeB talks with MME or S gateway or P gateway, etc. So at the moment, these are the 6 main pillars of Open RAN. These are: number 1, allows non-proprietary product and services. Number 2 is disaggregation. Number 3, allows open source features. Number 4, softwares and APIs. Number 5, cloudification. Number 6, AI, artificial intelligence and machine learning. Well, there is a small note for you all about the ORAN terms which generally used. ORAN with the hyphen in between is associated with ORAN alliances. Open RAN with the space or ORAN without hyphen sign refers to general term of Open RAN, and Open RAN without a space generally used by telecom infra projects, tip. Do not confuse, just memorize it, as all are working towards the enhancement of Open RAN and evolving the overall Open Radio Access Network ecosystem. Now, let's quickly talk about the communities and groups who are working towards standardizing the Open RAN ecosystem. I already told about the TIP, Telecom Infra Project, which is working towards the new innovations in the Open RAN system. Another ORAN community we heard is ORAN Alliances, which is developed by some of the big giant operators worldwide like AT&T, T-Mobile, Orange, NTT, etc. They are working to develop the open specification and standardizing them. Another form is Front Hall. They are a small cell forum and working to develop the front hall which connects the radio units with the distribution unit. In traditional RAN, this interface is currently proprietary interface. And this small cell forum has the goal to develop an open interface to replace the proprietary interfaces. There is one more community named as Open RAN Policy Coalition. They have the responsibility to create the generalized policies along with the policymakers, regulators and government bodies. This is very important before the deployment of any new feature and services and product used by the telecom industry and operators. Last but not the least, the another important community is ORAN software community, and you may already guess they have the responsibility to innovate the software development in the Open RAN domain. You might wonder, but software part going to play a very crucial and important role in the ORAN ecosystem. unlike traditional RAN, because traditional RAN is more focused on the hardware front and their development, but Open RAN will have more focus on the software front, and that is why ORAN Alliances is creating multiple softwares and features and functions with the collaboration of Linux Foundation. Now, in this session, we will understand the benefits of Open RAN deployment from the perspective of operators and telcos. Before we talk about the benefits of Open RAN ecosystem, let's quickly think about the problems and challenges with the traditional radio access network system. First, I will definitely say that existing RAN systems is highly capex driven. Any telecom network has three major divisions. One is radio access network, second is core network or switch, which is like data center, and another is transport division, which interconnects the radio access network with the core network. And the components used in the radio access network systems are one of the high capex contributing part. Hence, evolving the radio access network part will make the good impact on the capex. So with Open RAN, it can help to optimize the capex for the service providers. Same way, we are expecting to have the significant reduction in the operations expenditure too. This is because the ORAN ecosystem also have the goal to develop more and more automations to optimize the network with the help of new features and function development, and this will also help deploying the services faster. Traditional RAN systems are vendor locked, means operators are bound to use hardware, software, features, everything from the specific providers only. Means upgrade or swap between the ecosystems was a big pain. This gonna be completely flexible with the Open RAN ecosystem because of well generalized products. So operators can get the upgrades from the open source and can just implement it into the network without thinking of swapping the hardware, etc. Hence, the vendor lock-in problem will be solved with the Open RAN ecosystem. Because of this no vendor lock-in, operators and telcos will be in the stage to deploy any new features or functions more quickly. Means time to market will be really fast, because now telcos do not need to depend upon a single provider or supplier. They can choose who is solving the requirement in the best way, and operators and telcos will be in the stage to negotiate better, because now they are not dependent on the single suppliers anymore with this Open RAN ecosystem. Another important goal and expectation from the Open RAN ecosystem is to add more intelligence in the network with the help of deploying the AI, artificial intelligence and machine learning for better and on-time decisions. This will allow network to self-optimize for the future based on the historical data and predictions. So handling and operations will be more smart in the future. Okay, so we talked about some of the benefits of Open RAN ecosystems and the goals of Open RAN development, but there are certain challenges as well for the telcos and operators which they cannot side off. So one of the biggest challenges for the existing operators and telcos who are serving already and already have the huge infrastructure in place, the big worries to them is the integration with the legacy network. Because swapping the whole hardware and infrastructure and dumping the existing components is not a wise solution, because as I said, it was the biggest capex intensive part for telcos. So ideally, the Open RAN ecosystem should be fine with the legacy network systems, and this is really a big challenge. Another problem in the current time is that ORAN is not fully matured in present. It is still new and still in evolving state. So there is a worry for the telcos and operators to invest and deploy in the ORAN ecosystem until the Open RAN become more standardized and stable. To make it more generalized and also for supporting ORAN with the legacy network system, it is important to have the proper collaboration between all the vendors and sub-vendors, suppliers, providers, etc. to involve in the development of the Open RAN ecosystem so that multi-vendor support can be effective. Connectivity would be another main challenge because disaggregating of nodes in radio access network and disaggregating some functions also between nodes and backend is in the goal of Open RAN ecosystem. So there must be a strong solution to stabilize the connectivity and transport for different requirements, like applications or functions where the high latency is needed. Another big challenge is with the operations. This is because Open RAN will allow multi-vendor components in the infrastructure. So in the traditional RAN systems, the complete ecosystem is from one specific supplier like hardwares, softwares, interfaces, features, functions, etc. These all things belong to one specific provider and they own everything. So if network faces any difficulty in any way, then the problem is easy to identify because everything belongs to one supplier. And they have their experts to look into the issues and they know their systems from end to end. And for many telcos and operators, these vendors are also taking care of the operations too. So finding the issues and solving them is convenient for operators. But with Open RAN ecosystem, this will definitely change because now more than one suppliers need to involve to identify the RCA, root cause of the problems and fixing them. So operations gonna be little tough with ORAN ecosystem. However, this also can be addressed with the new features and function development to identify the defects and bugs in the components. Another challenge I will say is operational readiness because there are very less people who have proper skill sets for the Open RAN. It will not be exactly same as the current industry because we would be needing DevOps engineers for automations and upgrades and likewise many other profiles. In this section, we will talk about the architecture of Open RAN and traditional RAN. So, we will start from the high level of traditional telecom network first. We will also have the high level overview of traditional radio access network so that you can relate them when coming to ORAN part. We will talk about the evolutions in RAN like virtualization, cloudification, etc. We will talk about deployment strategies and scenarios which operators and telcos can have across the globe. We are also going to talk about the protocol layers in radio access networks. We will refer to the Open RAN architecture which has been defined by the 3GPP standards. We will talk about 3GPP split 2 which is on higher layer. We will also refer to the another Open RAN architecture that has been developed by the ORAN alliances. We will also talk about the SMO, Service Management and Orchestration, and RIC, Radio Intelligent Controllers in Open RAN. Okay, so let's start. In this session, we will understand high-level architecture of traditional network system and we will see a real-life radio access network system. In the screen, this is some high-level architecture of a traditional network system. So, as I said, there are three main sections of any telecom network. First is radio access network, RAN or RF we say generally. Another is core unit and there is transport section which interconnects RAN network and the core network. So as you see, radio access network is closer to the users, generally a mobile phone. We also say UE, user equipment, and all the user traffic and control traffic are transferred between the RAN network and the core network by the transport, which includes multiple hubs and many switches in between. The last section is the external part of the network like internet and PSTN etc. and all the data routed to the users from internet to core, then to RAN and then to UE. Let's have a quick example. So you as a user wanted to watch this video from YouTube from the telco network. Then UE or mobile will send the request. This request will go through to the RAN network and then reach to core network through the transport network, and then core network will look for the YouTube server and connect you through the YouTube server, and then the video content will be transferred back to the UE. Means from external network to core and then to transport network, then RAN network and finally reaches to the UE. So this initial part which is closest to the UE is consists of radio unit, which provides wireless connection between the mobile phone or UE or device with the network. And another part inside it is BBU, baseband unit. Generally, these BBU, baseband unit and radio unit are being supplied by the one supplier in the traditional RAN network systems because there is no compatibility with other vendors and suppliers. And there is no open interface between the multiple vendors. There is no agility there. All the hardwares and softwares belongs to the specific supplier only. So no flexibility, there is no disaggregation functionality in traditional RAN. Everything is preset in the hardware and software configuration. You cannot move functionality at different levels based on your needs. Hence, no control on the latency and other important factors. all the innovations and new development are just dependent on the supplier wish, because there is no third-party functionality is allowed. So, if some operator and telco wanted to integrate any new functionality, they are only dependent on their supplier in traditional RAN systems. They cannot use any third-party functionality and applications from other suppliers which can be easily available in softwares and IT space. But with the Open RAN concept, they will allow to use any third-party functionality and applications from any supplier. Anyway, in the screen, there are some real pictures of traditional cell or site. You can see them very easily around you. So there is a cabinet near the telco tower. This cabinet has the power supply system and backup system, and most important, you will find BBU, baseband unit, and radio unit inside it. In some cases, baseband units are set in the cabinet and radio units placed near to the antenna at the top of tower. Because this is traditional radio access network system, so this baseband unit architecture and the radio unit architecture are not open. They can only work together because their architecture is proprietary designed and shared between these two units only. There is no split architecture for BBU and radio unit, so operators don't have much flexibility here. In this session, we will be talking about the evolutions of RAN from legacy network to the cloud native networks. We will discuss RAN disaggregation and deployment strategies. Okay, so as displayed on the screen, these are categorized in 4 main steps. As I said, readiness is the important factor for deployment of any new concept, and for the existing telcos and operator, it is very unlikely that they step directly from the legacy network to the complete cloud native networks. Hence, doing that in steps would ease the whole process. So the first stage we consider the native or existing RAN infrastructure. So we assume that every existing telco operator is at this stage. So this is the first stage of radio access network, is very specific to a single supplier. Hardware, software, interface, features, functions, everything. This type of RAN systems are highly hardware dependent. KPI's dependency on hardware is also very high. These type of RAN systems are not super efficient in terms of resource utilization because of very limited features development and automation. This traditional RAN system required more planning for good balancing of resource utilization. They are expensive, they are complex, unpredictable, and maximum time over-provisioned in terms of planning of sites and baseband unit deployments. Because one baseband unit is very specific to one site only. There is no concept of pooling of baseband resources at central location from where they can tune the resource requirement for individual sites. So here the stage 2 comes, which is more towards the virtualization of a RAN ecosystem. So the native RAN network can be virtualized. Note that this does not mean that this is an open RAN system. Here the concept of virtual machine comes, where the software and functions can be deployed based on the requirements. So this stage includes virtualization of legacy hardware and hypervisor-driven architecture. At this stage, automations are very limited and maximum configurations are manual. Okay, now coming to stage 3. This stage is 3, one step up from the virtualization and focused more towards the cloud solutions. This stage have vision to introduce more and more automations in the functionalities and the operations, like resource scaling up and down based on the real-time requirements. This gonna help optimizing the utilization of the resources in the better way, because by adding these functions, sites are not allocated with the fixed resources. They can hire the resource in the dynamic environment and completely based on the real-time requirement, and that too from the central pool. And because of this flexibility, hardware capabilities will not be limited and KPIs are expected to improve. Because the sites with the heavy load who have resource crunch to serve all the user efficiently will now able to get the sufficient resources to serve their users. Hence user experience and KPIs both gonna improve. So hardware dependent KPIs are expecting to improve. Alternatively, you can say at this stage the network KPIs are less hardware dependent. Do you agree with me? Anyway, so in brief, this stage, which is cloud ready, will have more automation possibilities. Resource management would be easy, move towards software driven and API driven architectures. KPIs and qualities and user experience is no longer dependent on the hardware restrictions. This stage 3 has the ability to add more flexibility and more agility in the overall network systems. Okay, now the stage 4, which is the final target at the moment. This we call cloud native networks. This will allow containerization and orchestration and going to allow a lot of automations and self-driven decisions to configure and reconfigure the network parameters to improve the overall network performance and user experience. This stage 4 is targeted to self-discovering the network issues and optimizing them and fix them as well. That too without direct human intervention. This will allow self-scaling and adjusting the resources based on the real-time needs and all with the help of AI, artificial intelligence and machine learning. They would be able to predict the future requirements and can take on-time and better decisions to overcome any real-time complications, etc. Isn't super excited? Yes, I am very excited to deploy this level of intelligent system and features and functions in the network. And this all possible because now many third-party application developers and product managers can work towards a specific goal. And once they give the proof of concept, every telco operator can use that in their network system. They do not need to wait for their service provider or supplier to develop that. Hence the evolution in the RAN network systems gonna be increased multiple folds. Okay, so in brief, cloud native stage gonna add more flexibility and agility to the network systems. Systems will be able to perform better in the dynamic situations and environment. The network will be able to find network issues by self and they're gonna able to even fix them as well. Auto scaling of the network will help to optimize the resources and can provide the better user experience and will improve the network KPIs as well. More and more AI and machine learning model deployment is possible, which will allow not only the real-time performance gain, but can take better decisions for the future based on the prediction models too. We understand that how the operators can move from the traditional radio access network system to advanced cloud native RAN systems. We discussed about the different stages which can help operators to gradually upgrade their ecosystems. Now, before going deeper, let's look over the traditional radio access network cell and site area. Then we will have some overview of traditional RAN and how the evolved Open RAN gonna different from the existing RAN systems. Okay, now let's have some overview of traditional RAN and how evolved Open RAN going to be different from the existing RAN systems. First, quickly see the traditional RAN system. Here, this is the BBU, baseband unit. That also includes the radio unit. And this is the core network part like EPC, Evolved Packet Core, includes MME, HSS, SWW, PGW, likewise. And there is the connectivity with the external network. There is a backhaul for the connectivity between the RAN network and EPC. This is just a high level, we are not going in deep today. Now coming to the evolved RAN part. Here we take the general reference of 5G NR or 5G new radio network or called 5G RAN. We can see the DU, distributed unit, and the CU, centralized unit. These are the two main parts who acts like the same as single BBU unit in the traditional RAN system. These two units can be split and can be placed at two different positions in the site based on the type of BBU units. Same we do in the traditional RAN systems as well. Again, depends on the type of physical units. If they are separate, BBU unit can be placed near to cabinet and radio unit can be placed near to the antenna. In the evolved RAN, we can see the virtualization is enabled in the network at CU, centralized unit. You can also see the cloudification here for G-Node B centralized unit and UPF. So there are multiple centralized unit here in the pool and they can distribute the resource to the individual sites and cells based on the requirement. And this way makes the resource utilization more efficient. This cloudification also allows the edge computing which introduced after disaggregation of radio access network. Now because distributed unit and centralized unit are separated as you see in the picture, there is a connectivity needed between these two units. This we call mid-haul. We will talk about that later. There is a front haul too, which we call eCPRI. Okay, this was some high-level overview on the stages and evolutions of RAN and high-level architecture of evolved RAN system. Now quickly understand how telcos and operators can go forward to the acceptance and deployment of ORAN in their networks. Well, as I said, the transactions from the legacy network to the ORAN is not just like one go, but it needs to be happen in stages. So instead of jumping to the Cloud RAN street, telcos and operators can prefer to deploy the virtualization in the distributed RAN initially. So with this scenario of distributed RAN, both the units, means centralized unit and distributed unit, kept at the cell or site area. With this approach, there will not be a huge shift in the hardware part, but this will allow the customization from the software front. Means operators can add or manage the new features and functions at cell or site level with the help of softwares, and that too on the same hardware. At the next stage, operators and telcos can move to the centralized units away from the cell or site, and they can deploy the cloud-based centralized unit. This cloud-based centralized unit is able to serve more than one cell or site in the network, and based on the resource requirements, this cloud-based centralized unit will allocate the resources to the respective cells or site which are connected with that centralized unit. However, the distribution unit is still present at the cell or site area. Hence, we need a connectivity between the cloud centralized unit to the cell or site distribution unit. This mid-haul interface or connectivity introduced when the split architecture planned for distributed unit and centralized unit. For good and stable connectivity, this mid-haul will connect the centralized unit and distributed unit through the fiber line, which some operators can own or some operators can hire on the lease too. However, this is not only limited to the wired connectivity. Wireless mid-haul is also an option. So the centralized unit will be placed at some central location of multiple cell or site, and all the cell or site will be connected through a mid-haul connectivity, and all the cell or site will have the shared resources pooled at the centralized cloud unit, and they will get the resources based on the requirement. There is one additional option where both the units, means centralized unit and distributed unit, will move to the cloud area at one specific central location, and all the cells and sites will have the connectivity between their radio units and centralized distribution unit. So operators can choose any preferred solution they want based on the type of services and offerings. In this session, we will have some high-level overview of protocol layers. Each radio access network has mandatory protocol layers, like traditional 4G network protocols are in the left, in the Open RAN network in the right for 5G NR. You can see in Open RAN, some of the protocol layers are disaggregated from the standard one. These pictures are just for reference. So in the traditional RAN systems, like in 4G in the picture, there is a baseband unit who actually handles these all protocol layers like physical layer, MAC layer, RLC layer, PDCP layer and RRC layer. At the same time, you can see the evolved 5G ORAN network where some layers are disaggregated to the distribution unit and some layers to the centralized unit. Similarly, some functionalities which required low latency to act, they kept close to the users, means in the distribution unit, and other functions like registrations, initial access, QoS can be handled from the centralized unit. So from the high-level overview, in evolved 5G RAN, physical, MAC and RLC functionalities being handled by the distribution unit, and PDCP, SDAP, which is newly introduced protocol layer in 5G, and RRC layer are being handled by the centralized unit. This is the example of disaggregated RAN, where some of the functionalities are being disaggregated from one unit to another unit. So the radio units handles the RF, radio frequency related functionalities like analog to digital conversion or vice versa. Radio unit is also responsible for lower physical layer task handling like time and frequency conversions and vice versa. Distribution unit takes care of the higher physical layer tasks like modulation of signal, coding of signal. Distribution unit handles the scheduling of data, HARP management, multiplexing, demultiplexing in the MAC layer. Also take care of RLC responsibilities, automatic repeat requests and segmentations. Whereas centralized unit includes PDCP layers, means it handles the header compression, security and QoS flow handling in 5G. Security and QoS flow handling is being handled through the SDAP protocols in 5G. Centralized unit also handles the most important control layer, which is L3 or RRC layer. This layer handles the attachment of users with the network, accessing the services, handovers, activation, deactivation, RRC configuration, reconfiguration, etc. We will talk about them later, but all these things happens in the centralized unit. Now, if you look into the ORAN architecture from the protocol layer perspective, you will see there can be many options of disaggregations and shifts of layers. When 3GPP introduced this architecture, they suggested option 2 can be carried out for the evolution of ORAN. However, there are more options in this shift, as you can see from option 1 to option 8. But the important shift or split which was introduced by ORAN alliances as ORAN 7.2x is option 7. The basic idea of making this split is to separate the higher physical layer and the lower physical layer. So after this split, the lower physical layer will be near to the radio units and higher physical layer will be near to the distribution unit. And by doing this, the radio unit size gonna be reduced, and this will ease the deployment process too. Another important evolution in the ORAN is introducing the RIC, Radio Intelligent Controllers, and orchestrations and automations. These are introduced by the ORAN alliances. Radio Intelligent Controllers and orchestrations developed for two different functions. RIC or Radio Intelligent Controller further subdivided into real-time RIC and non-real-time RIC. The functionalities of these real-time or non-real-time RIC can integrate based on the different applications. These can be third parties as well. So these third-party tools can collect the information from the centralized unit and distribution unit and can decide and adjust the parameters and features of the network to provide the optimal services and the high-quality user experiences. Any application which requires to respond in the real time means where the latency plays the important role, they can be integrated in the real-time RIC, and if any functionality can be managed at non-real time, they can be integrated in non-real-time RIC. This means near real-time RIC can be placed near to the regional area or centralized unit area, and non-real-time RICs can be placed in the data centers or switch areas, etc. So now, these third-party applications are responsible for the mobility management, maintaining the quality of services, optimizing it, optimizing the antenna functions like MIMO, beamforming, etc. This can also manage the radio resources in the wider area in very efficient manner, unlike in the traditional systems at cell or site level. So these are the common functionalities I have mentioned here, but this is not limited to them. Telcos and operators can add many new functions and the new features from the offerings of these third-party applications. Another important announcement is orchestration, which will help to configure and design the radio access network very quickly, unlike in the traditional RAN, where this designing and the configuration is a long procedure. ONAP is working on this, which is the another community in ORAN and part of Linux Foundation. ORAN alliances introduce few more interfaces in the architecture like O1 and E2, etc. in the picture. These interfaces provide the connectivity between the distribution unit and centralized unit to RIC and orchestration. Okay, now let's talk about little on the SMOs. SMO is Service Management and Orchestration. As we had some high-level overview of ORAN Alliance architecture, we seen Service Management and Orchestration, and we seen some new interfaces. Let's talk about some of them. In real-time RIC, for RAN optimizations, F1 interface is introduced to provide the optimization related information to real-time RIC from non-real-time RIC. FCAPS is the another interface in ORAN entity which is done by the SMO. This can help configuring the new sites faster and can help in fault identification, accounting and security. And O1 interface is introduced for this job. Another important interface is O2, which is introduced in ORAN Cloud Management and Orchestration. This interface helps in cloudification of ORAN. Let's have a quick overview of working groups who are working towards the evolution of ORAN. These are some of the impacting working groups in the domain of ORAN. I will read it thoroughly. Some of them are working on SMO, some are working on RIC, some working on the front haul and some working on the protocols, etc. So WG2, non-real-time rate controllers, and WG6, cloudification and orchestrations working on SMOs. WG3, near real-time rate controllers working on the intelligent controllers, and so on. You can refer to this page for details. In this session, we will talk about the Open Distribution Unit and some of the functionalities of ODU. So far, we've seen that Open Distribution Unit have some responsibilities of Layer 1 functions as well as some of the L2 layer functionalities. L1 or Layer 1 is the physical layer, and understanding of resource allocations in the physical layer, like in the time domain and frequency domain, is very important. In this session, we will be talking about that, and in the upcoming session, we will cover the different type of channels like control channels and shared channels, etc. and control signals. We will also talk about how the data and signals being transferred between layers and provide end-to-end connectivity in the downlink and uplink. Okay, let's see how the physical layer looks like in the time and frequency domain. This structure is 5G physical layer structure and numerology is 15 kHz. So you can see here that each and every resource is distributed individually in the time and frequency domain. For reference, view from the top is the time domain and view from the side is the frequency domain. One system frame is of 10 seconds and we are considering one subframe here which is of 1 second. This subframe again subdivided into slots, and these number of slots are depends on the numerologies in the 5G that you can see from the table in the screen. Note that each slot consists of 14 OFDM symbols. So numerology 0, subcarrier spacing is 15 kHz. This is same as in LTE. Number of slots per subframe is 1. Number of symbols per slot is 14. So you can calculate the total number of symbols per subframe easily. I have listed them in the table already. The total RB size also calculated in the last. So for numerology 1, subcarrier spacing is 30 kHz. Number of slots per subframe is 2. Symbols per slot is 14. And total symbols in the subframe is 28. RB size would be twice of 180, means 360 kHz. Similarly, for numerology 2, subcarrier spacing is 60 kHz. Number of slots per subframe is 4. Symbols per slot again 14. Hence, total symbols per subframe is 56. And RB size would be 720 kHz. Similarly, you can map for numerology 3 and 4 and for later releases too. To have the better understanding of physical layer mapping, there is must to understand the concept of basic building blocks of the resource blocks, which I would be covering separately, so you can stay tuned for the updates by subscribing us, and do not forget to press the bell icon too. But in short, each resource block builds from the slot in the subframe, means in the time domain, and 12 subcarriers in the frequency domain. These resource blocks are distributed among the different type of logical signals, control signals, and shared channels, etc. Like you can see the PSS primary synchronization signal and SSS secondary synchronization signal and PBCH physical broadcast channel, etc. These are being used for the initial access procedures, as PSS and SSS being used for the cell search procedures and identification, radio frame timing information, etc. MIB master information block is carried through the PBCH channel, which is required for UE to access the network. Beyond here, all the signals and channels you see in the picture are being served by the ODU Open Distribution Unit. This includes PDCCH, Physical Downlink Control Channel, which is being used for DCI, downlink control information. It carries scheduling information, HARC information, etc. PDSCH, Physical Downlink Shared Channel, used for carry the user data and also for the SIB messages. There are more channels too for sync, like DMRS, Demodulation Reference Signal, which is used to have the estimate of the other channels like PBCH, PDSCH, PDCCH. Another is CSIRS, Channel State Information Reference Signal, which is used for CQI calculations, recoding matrix, rank indicator information, link adaptation information, etc. We will going through the physical layer architecture of ODU. If you have the understanding of 5G NR physical layer structure, then this will be easy to understand. So in ODU, there are some physical common control channels and also shared channels. These will be in the downlink and the uplink as well. There are some reference signals, You will also see PDCCH. PDCCH, Physical Downlink Control Channel, carries the downlink control information like the information for scheduling and resource grant to the UE, etc. PDCCH carries the information of resources which need to be allocated to the UE. PDCCH can have one or more CCE control channel elements, depends on the aggregation label used in 5G. We marked 5G here because this was introduced with the 5G NR technology, which allows higher bandwidth and spectrum for heavy broadband services. In LTE, there was no such aggregations. So you can consider that there is only one aggregation label, or CCE means 6 RBs in LTE. But in 5G, you can have aggregation label like 1, 2, 4, 8, 16, and respective RB requirements are 6 RBs, 12 RBs, 24 RBs, 48 RBs, 96 RBs. Another important factor is core set, control resource set. PDCCH has different functions as I listed some here. PDCCH is used to notify the UEs about the formats of slots. PDCCH also takes care of the transmission of power control commands for PUCCH and PUSCH channels. PDCCH also takes care of active bandwidth part switching for the UE based on their demands. Now let's talk about the physical shared channel in the downlink, which is PDSCH. PDSCH mainly carries the user information in the downlink. This user data gets transferred in the terms of transport blocks, or generally called TBs. These are also called the data payload. So the information comes from the upper layers like MAC layer. From MAC layer, user data comes in the terms of transport blocks or TBs. When these transport blocks carries down to the layers in the downlink, there are some mandatory actions which need to be followed. For example, CRC is added here at first, also called cyclic redundancy check. Why the CRC check? So the information in the TBs which are coming from the higher layers, CRC will check the information for any error. So if there is any error detected, then some type of error correction methodologies will work, like here LPDC, which is low density parity check codes. So LDPC will try to correct the information with the help of parity checks likewise. The next stage is rate matching. This will match the frame size of transport blocks from the higher layers like MAC with the lower layers. Here the HARC hybrid ARQ will also work. If any information is repeated in the transport block, then it will notify that the information is not needed to be resent. HARC also work out when any information in the transport block is not received completely, and in that case will ask the higher layers to resend the data again. Then the next step would be the scrambling, which provides the interference protections and privacy for the transmitted data. It plays an important role in securing the secure and reliable communication of information between the base station, means G node B, and the user equipment, UE or device in the 5G network. When there are many different cells reported with a similar signal strength, then this identifies that which PCI to consider and which PCIs to ignore, so that interference won't impact much. Next stage would be the modulation. In NR5G, the UE can be allocated any modulation scheme from QPSK to 256 QAM or even higher like 512 QAM or 1024 QAM in the future. This modulation scheme is allocated depends on the type of size of user data requirement, also depends on the radio conditions of course, but whatever the modulation scheme is final, the user data or the transport blocks will be mapped to the respective modulation scheme in the lower physical layer through different multi-antenna precoding. Let's quickly talk about the reference signals as well in the downlink. There are different types of reference signals which are being used for different perspectives, like demodulation reference signals DMRS, phase tracking reference signals PTRS, and channel state information reference signal CSI-RS. These reference signals are being used for the channel estimations in the downlink. Downlink reference signal DMRS is used to have the estimation of signal strength and what is about the channel quality. Phase tracking reference signal is used for compensating the phase noises, especially in a very high frequency bands and millimeter waves and with multiple antenna array structures. CSI-RS channel state information reference signals received by the UE, and it tells about the estimation of interference. in case of advanced antenna concepts like multi-beam, massive MIMO, etc., where beam management need to be done. Likewise, we had some brief of common control channels and shared channels in the downlink in the last session. In this session, we will understand the common control channels and shared channels in the uplink quickly. So, common control channels in the uplink is called PUCCH. This channel carries the information of different users. Those are sending the information from device to the base station. This information can be anything like scheduling of transport blocks and resources. Also, this can carry the feedback information which device need to be sent back to the base station like ACK or NAC information of the received data. It also tells the HARC feedbacks like what data need to be resent, etc. HARC is Hybrid Automatic Repeat Request. PDCCH also takes care of modulation schemes which can be used by the multiple users from the multiple devices. Means if some user needs the higher modulation scheme based on his high data uses in the good RF conditions, then the scheduling can be happen by this PUCCH in the physical layer. PUCCH also takes care of the PRB allocations because wireless network has the limited resources and that need to be distributed among all the users. So this is one of the important role that is handled by the PUCCH. CSI or the channel state information gives the information about the channel quality. This is important information because that tells how the allocation of resources can be planned for all the users. Also, if the channel quality is good, network will need the less resources to transfer X amount of information compared to transferring the same amount of data in bad radio quality conditions. PUCCH also supports multiple formats, depends on the OFDM symbols. These are some combinations which are being used to allocate the PUCCH resources in the resource blocks, means in the time and frequency domain in the physical layer. So some criteria is like how many symbols we wanted to fix or allocate for PUCCH, how many UEs or devices we are planning to cater with the cell, those all the UEs or devices normally multiplexed on the same channel. So in short, PUCCH is planned for any cell. So if short PUCCH is planned for any cell, then format 0 or 2 can be used. These uses less resources for the PUCCH channel from the PRB structure in terms of resource elements in time and frequency domain. But if the need is to cater many user devices whose data are about to multiplex in the resource allocation, then we require the long PUCCH, and for that format 1, 3 or 4 can be used. This will allow more users to have multiplex resources in PUCCH from the PRB grade, means more users can be served. Also have the more resources to serve the users at the edge of cells. In other words, you may also hear that the long PUCCH gives more coverage and stability. It is not because the radio coverage increases, it is because having the more resources have better redundancy and ability to cater to more users. Similar to PDSCH, shared channel in the uplink means PUSCH carries the user data which needs to be transferred from device to the base station. The steps in the PUSCH are just reversed from the steps in the PDSCH. Means in PDSCH, user data comes from the higher layer like MAC layer and passes to the lower layer. But in PUSCH, user data or the transport blocks received at the lower layers at G node B like physical layer means from the antenna mapping, then resource mapping, modulation schemes, coding and rate matching, then the CRC checks and HARC indicators, etc. In the last few sessions, we had some brief of different type of channels and physical layers which is being catered by ODU. In today's session, we will be talking about the layer 2 protocols which are also being handled by the ODU, Open Distribution Unit, other than the higher physical layer functionalities which we discussed. If you look over the screen, there are 4 protocol layers in the L2 layer, which is data link layer, and these protocols are SDAP layer, PDCP layer, RLC layer and MAC layer. Out of these 4 layers, MAC protocols and the RLC protocols are being handled by ODU, Open Distribution Unit, which we will be talking about. As I said that these protocols have their own responsibilities, means they take some data from the higher layers, process the data and pass to the next protocol layer. At RLC protocol, data comes from the higher layer which is the PDCP layer and go down to the MAC layer. RLC protocol layer receives the information about the radio barriers from the upper layer. RLC uses the logical channels to transfer the data which will later map to the physical channel as well. RLC mainly do the segmentation of SDU which is Service Data Unit. which is being requested by the MAC layer and then sends the PDU protocol data units to the MAC layer. Do not confuse. In general, when any information which is being transmitted from one layer to another layer, then it happens through the SDU, service data unit. And when the information is within the same layer, this data is to be transmitted as PDU, protocol data units. Simple. The RLC sublayer provides TM data transfer, UM data transfer, and AM data transfer, including identification of successful delivery of upper layer PDU services to RRC or PDCP. RLC layer is responsible for error correction. It uses ARC, automatic repeat request. RLC do the segmentation and desegmentation of the data. There are few different ways how the data can be transferred in the RLC. These modes are TM mode, transparent mode. Second is UM mode, unacknowledgement mode. And third is AM mode, acknowledgement mode. So TM, transparent mode, there is no RLC headers, buffering at TX only, no segmentation and reassembly, no feedback, that is no acknowledgement. UM uses RLC headers, buffering happens at both transmission and reception, responsible for segmentation and reassembly, and there will be no feedback like ACK or NAC. AM, acknowledgement mode, there will be RLC headers, buffering at both transmission and reception, also do the segmentation and assembly, and it will have the feedback like ACK or NAC. So TM mode, transparent mode, as you see that in TM mode there would be almost no processing to the RLC data. The only thing that it does is to buffer the data on the transmission side. There is no RLC headers, no reordering, no segmentation, no reassembly is happening in this layer. And because of this, no data processing nature of TM mode. If you compare the RLC input and the RLC output data of TM mode, you won't see the much differences between two. Now second is UM mode. So UM stands for unacknowledged mode. Unacknowledged mode means it does not require any reception response from other party. This means simply that ACK or NAC is not being received from the second party. Last is AM mode. So if you look at the AM mode, this is the most complicated RLC type. AM stands for acknowledge mode, and as its name implies, it requires acknowledge and negative acknowledge from the other party. Another function of ODU is the MAC layer function. MAC layer is responsible for the scheduling of data. MAC layer is also responsible for the management of HARC, where error detection and correction is required. MAC layer takes care that how the resources will be allocated in the downlink and uplink. MAC layer handles the multiplexing and demultiplexing of the MAC STUs. MAC layer also prioritizes the logical channels. So this was just a brief. In this session, we will talk about the another important component of Open RAN, which is Open Centralized Unit. Central unit in the Open RAN has the multiple responsibilities of layer 2 and layer 3. From the layer 2 perspective, Open Central Unit takes care of PDCP protocol, which is Packet Data Convergence Protocol, and SDAP protocol, which is Service Data Adaptation Protocol. And from the layer 3 perspective, Open Centralized Unit consists of radio protocol architectures and takes care of RRC, radio resource controls. RRC is one of the most important protocol needed to establish and maintain a consistent connection between the end user device and the network. Okay. Let's start from the L2 functionalities of Open Centralized Unit. So you can see the 4 protocols of the L2 layers over the screen. Out of these, we talked about the RLC and MAC protocols, which are actually being catered by the Open Distribution Unit. SDAP and PDCP are the protocols which are being handled by the Open Centralized Unit here. So you can see that how the data is being transferred from MAC to RLC to PDCP to SDAP. Each protocol layer adds some additional information over to the received information, which also called the header bits, and then pass it to the next protocol layer. So here data is coming in terms of IP packets from the upper layer. You can see layer 3 here. This data traveling in the layer 2 as a SDU, service data unit. These all information are encapsulated in a kind of radio barrier. So you can see that the IP packets are encapsulated in multiple SDUs, and they are combined in the radio barrier. Means one radio barrier can combine more than one SDUs or IP packets. And later these are converting into the transport block at the MAC layer. This is just a high level that how the data flows from higher layer to the lower layers. Let's talk about some of the basics of the PDCP protocol. PDCP is Packet Data Convergence Protocol. PDCP protocol provides services to both the control plane as well as the user plane to the upper layers or higher layers, where RRC is basically used for the control plane information and SDAP is used for the user plane data. PDCP protocol is responsible for header compression or SDU, service data units. PDCP layer also checks for the integrity protections and uses SIPRing for security. In the last, PDCP headers gets added in the SDU and remove any kind of duplications. Now the data will move to the lower layers and gets transmitted to the another point, where PDCP protocol receives that information. Here now the PDCP layer will do the de-SIPRing and PDCP layer will discard any kind of duplications and reorder the SDUs in the right form. Then PDCP layer decompress the header which was added during the header compression stage earlier, and then it will send the original data back to the higher layers. If you notice, then at receiving end it reverses the actions which was taken at the transmitting end. PDCP works for both control plane and user plane, depends on the type of radio barriers coming from the higher layers. PDCP also plays the important role in DC. DC is dual connectivity mode and it can be associated with one or two or more RLC entities, depends on the type of multi-connectivity barrier. So in dual connectivity, PDCP provides the different radio barriers for master cell group and secondary cell groups, and these radio barriers in the multi-connectivity mode handles by the PDCP layer. SDAP is the another protocol which is handled by the Open Centralized unit. SDAP is Service Data Adaptation Protocol. This is responsible for the QoS flow handling across the 5G air interface. We specifically mentioned 5G here because it was introduced with the 5G evolution. It was not available with 4G or LTE. It receives the packet from the higher layer and adds up the QoS flow ID with each and every packet before forwarding the SDU to the lower layers. In the screen you can see how the packets are being transferred between the UE device and the G node B through the radio barriers. Each packet here is being assigned with the QFI. I have also added the UPF part here, which is actually a core network function, but this is how end-to-end QoS looks like in 5G. SDAP structure is configured by the RRC. The SDAP layers maps QoS flow to the DRBs. The SDAP sublayers maps the QoS flow to the DRBs. One or more QoS flows may be mapped onto one DRB, but one QoS flow is mapped onto only one DRB at a time in uplink. The SDAP entities are in SDAP sublayer. Several entities may be defined for a UE. There is one SDAP entity configured for each individual PDU session. We talked about the L2 responsibilities of the Open Central unit, which are PDCP and SDAP protocols. In this session, we will be talk about the L3 responsibilities of Open Centralized unit. We will talk about the radio protocol architecture and RRC. We will also brief the states of RRC. So this is the high-level architecture of protocols, and this shows that how the data gets transferred from higher layer to the lower layer. This is the diagram of the user plane. As I said that SDAP is only used in the user plane, and when we talk about the RRC, then it is completely the control plane information. So SDAP, we talked that the IP packets coming from the upper layer, SDAP protocol add the QFI information on those packets and then forward the packets to the lower layers through the radio barriers. Then the PDCP have the responsibility of SIPRing and header compression. PDCP also do the disaggregation of different radio barriers for master and secondary cell groups in case of dual connectivity or multi-connectivity mode. Then those SDUs comes down to the lower layers, which is RLC protocol, and then more down to the MAC layer protocol, where these IP packets and radio barriers gets converted into the transport blocks. If there are multiple carriers serving, in case of carrier aggregation, which is very common in 5G and also used in the 4G, then MAC has the responsibility to manage the aggregation of data between the carriers. And then these transport blocks are being transferred down to the physical layer, which will map the transport block into the physical resources in the frequency domain and the time domain for the transmission of data. It also includes mapping of information based on the modulation schemes, beam informations, etc. So this is how the data flows in general. If this is clear, then let's talk about the RRC layers. So RRC is Radio Resource Control Protocol. This is the L3 layer or network layer in the OSI model. RRC only contains the control information, means no user data or payload transferred over the RRC protocols. RRC protocol responsible for initial setup and access of network. It is responsible for connection establishment between the UE and the base station. It is also responsible for release of connection. There are different broadcasts of the system information which is being continuously broadcasted in the downlink by the base station, which tells users about the network. RRC is responsible when users wants to move from one cell to the another cell. RRC tells users that what are the different criteria of hand in or hand out, what are the criteria of even selection of a cell, like we call the cell selection and deselection. RRC tells about the need of radio barriers and helps in establishing the radio barriers between the UE and network. For the configuration and reconfiguration of any stage for any services, RRC is mandatory. From initial registration to the access of service, from paging to notification, changing in services, addition of carrier aggregation, new carrier configuration, all the steps are being handled by the RRC. This also takes care of the power control, means it guides the UE and the base station that at what optimum power UE should transmit the information depends on the radio conditions. Now you think it right that this is one of the most important protocol to understand. If we talk about the general stages of RRC, then these are RRC idle, then RRC inactive and RRC connected. However, 4G mainly have the RRC idle and RRC connected, but 5G also have the RRC inactive state as well. So in RRC idle mode, there is no direct connection between the UE and network, just high-level tracking information is available. No data transfer is possible when RRC is idle. There is no RRC context and there is no connection of UE with the core network. In the case of RRC connected mode, UE and network has a valid established connection and radio barriers through which the data transfer is possible, either a voice call or payload data, anything. Let's talk about the registration management and the connection management. As this is very clear with the name that registration management, it basically starts the registration of the UE with the core network. After the UE registration is complete with the core network will have all the valid locations and routing related information of the user. So once the registration is done, it is called RM registered mode, else it is RM deregistered. Next is connection management, which comes in picture when UE require the NAS signaling connection with the AMF. The states can be CM idle or CM connected. So the UE is in the RRC idle, then at that time there is RM deregistered and CM is also idle, means there is no connection between the user and network, and hence no data transfer is possible. There is no RRC context is enabled at that time and there is no connection with the core network. Cell reselections happens by the UE when they are moving from one cell to another. That happens by absorbing the same information transferred by the G node B in the downlink. But now when the RRC is connected, this means RM registration is done and AMF also have the information of UE location. Also when RRC is connected, this means the CM is also connected for NAS signaling between user and core network. Established a connection does not mean that the data is transferring actively. Hence, this new stage comes when there is established connection between the user and core network. This means RM is registered and CM is also connected, but there is no flow of user data or payload. There is RRC context established, but no user data flow. This stage is called RRC inactive. The benefit of RRC inactive is whenever there is any need of user data flow between UE and network, the data transfer can live in very minimal time because the connection is already exists there, hence the response time and the latency will improve. Because the steps of RM registration and CM connection is no longer needed from the very start of service because it is already there. You can relate it with the very simple state machines in the screen. So at first UE is powered up. So it will be in RRC idle mode, means there is RM deregistered and CM is also idle. Now the RRC connection request made and the state will change to RRC connected. Now if because there is no user data transferred live, it will move to RRC inactive stage. If demand of user data barrier comes, it goes back to RRC connected stage. If connection fails at any point of time, then it will go back to the RRC idle state. When the state is RRC connected, then if RRC release request is received, then it will go to the RRC idle state. Also, if RRC connection fails at any point of time because of any reason like radio condition, it will again go back to the RRC idle state. During the RRC connected state, if RRC suspends, then it moves to the RRC inactive state, and if RRC resumes, then again it goes to the RRC connected state. Simple. In the last few sessions, we had little understanding about the protocol mappings with the Open RAN units. Now we are introducing concept of AI, artificial intelligence and machine learning in the Open RAN systems. Such labels of intelligent systems and controllers was not available with the traditional RAN systems, but with the engagement of AI and machine learning, these intelligent controllers and radio access networks gets evolved and become more efficient. We will start from the absolute basics and gradually increase the labels so that you can start from the label which suits you best. We will start from the basics of machine learning. We will talk about different concepts of machine learning like supervised machine learning, unsupervised machine learning, reinforcement learning. We will talk about the machine learning models and the training of machine learning models so that these models can be utilized in the Open RAN systems. We will talk about the real-time RIC, radio intelligent controllers, and non-real-time RIC, how these units can optimize the open radio access networks and improve the efficiency of the network with the help of machine learning models and third-party solution. So, what is machine learning? Machine learning is one of the most important part of bigger umbrella known as artificial intelligence. Machine learning is the concept where machines can automatically learn from the data and the past experiences. They use the data to identify the patterns, and based on that, they are able to make predictions. These patterns and logics are not hard-coded in the softwares, but the machines develop them automatically by analyzing the patterns in the input data and by their past experiences. We needed machine learning concept to handle any new situation that arrives. The existing software models are good enough to handle the predefined situations with the pre-programmed logics, but they are not efficient in handling of the new environment or condition. To improve that situations, we humans are needed to change the existing codes of softwares or functions. But machine learning models are able to predict better solutions on those situations. That too without direct human interventions, based on the prediction models from the training datasets and previous good or bad experiences. Let's understand it with the example. Suppose you have been asked to develop a system which can tune the network for the throughput based on the signal quality. So you will need a lot of data related to the throughput and the quality of signals. This training data is generally called as training dataset. Once this training dataset is fed into the machine learning model, then the model will develop some patterns between the signal quality and throughput. And machine will create the relation between the signal quality and the throughput. And it will know that how the signal quality can affect the data throughput. So once this machine learning model is developed, who actually knows that how the throughput is affected by the signal quality, then this model can be used in any RAN system to predict that what would be the possible throughput for any specific signal quality. This is just a one function, and this is a very simple idea. However, as a network engineer, you know that throughput is not only depends on one factor, so other factors are also equally important. This means we needed a more complex machine learning model which would be able to handle different factors. These factors are called functions. One machine learning model can have 1, 2 or 3 and up to n number of functions. Now, because all the patterns are being developed by the machine learning algorithm based on the training dataset, so this is very important to have the good dataset for the training. If the training dataset is bad or not enough, then the machine learning model will not function correctly, like the example of garbage input and garbage output. In this session, we will have some overview of different type of machine learning models. This is important so that you can know that what type of machine learning models you will be needing for any specific job in intelligent system development. So first is supervised learning. In supervised machine learning, machines develop the patterns from the labeled dataset. Now, what is this labeled dataset, which is the input to the supervised machine learning? Labeled dataset is the set of data which has the input, and that input is also marked with the correct output. Means all the input data is tagged with the correct output. Once you have this labeled data as an input to the training model, it will develop the patterns between the inputs and outputs. This type of machine learning models you can relate like a teacher is giving some set of examples to explain any concept to his students. So students grab those examples and they will build some patterns in their mind to understand the concept which teacher is actually telling. Note that what examples are giving is still depends on teacher. If he gives the wrong examples, then students may build the wrong concept in their mind. So good data and sufficient examples is the key requirement of supervised machine learning models. Now, based on the prediction types, supervised learning is further categorized in classification task and regression task. So first we will start from the classification task. Classification tasks are used where the output can be classified in some finite classes. This is further subdivided into binary class classification and multi-class classification. Let's understand with some examples. So binary class classification has only two possible outputs like yes or no and true or false. Or you can say either the output can be this or that. Means only two possible outputs. Whereas multi-class classifications are the models where the outputs can be more than two. Each possible output belongs to one specific class. Like you wanted to know that if the UE or device is connected to internet or not, then the output can be either yes, means device is connected to the internet, or no, device is not connected to the internet. This is the example of binary class classification. Now suppose you wanted to know in which technology UE is connected, then it will be the example of multi-class classification because device can be connected through the GSM network or the CDMA network or 3G network or 4G network or 5G network, right? So this is multi-class classification. I hope I made it little clear to you now. Let's talk about the another type of task under the supervised machine learning, which is regression task. Regression task is being used where you cannot classify the output in a specific category. The output can be anything from a sequence number, like for example, prediction of the price of any item. So that price can be anything. Let's take another example from the network perspective. So you need to predict the PDSH throughput of a cell. This throughput can be in any range from a continuous number. You cannot specify this throughput in any specific class because this throughput can be in any range from a continuous number. However, this will be dependent of multiple factors, means we'll need different functions to have a good fit model. But as I said, you cannot classify the output in any specific category. So for developing such type of models, you will need regression tasks. These regression tasks can be further subdivided into linear regression, non-linear regression, and few more, depends on how inputs and output relations are built. Note that these functions are some type of mathematical functions which can fit the inputs with the respective outputs. So if the inputs and the outputs relation is linear, then it will be a linear regression model. But if that is more complex and not following the one linear line, then the machine will need more iteration of learning to have a good fit model for non-regression tasks. Now in this session, we will be talking about unsupervised machine learning and reinforcement learning. So what is unsupervised machine learning and why we needed it? As we mentioned that the labeled data is the most important ingredient in the supervised machine learning, which is actually not an easy task to have. Sometimes it is very expensive or time taking to collect the good training dataset and required lot of steps from cleaning of data to finalizing the training dataset. So here is the concept of unsupervised machine learning comes. In unsupervised machine learning, we do not need the labeled dataset. So the question is that how unsupervised machine learning works with the unlabeled data. So here is the concept of clustering comes when you provide lot of sample data to the machine learning model for which the output is not known. The machine learning model identifies the common factors in the input data. However, the output is unknown, but the machine learning model will know that something in the data is common, and based on that common factor, machine learning model will segregate the input data in some groups. These groups are normally called clusters, and the machine learning model will give some ID to the specific cluster. Means at the output of unsupervised machine learning model, you will have the output where each input data point are grouped with the other data points based on some common factors within those points. You can understand it with a simple example in the screen. Another important type of machine learning is reinforcement machine learning. This is the completely different approach from what we have learned because this machine learning model do not use any type of labeled or unlabeled data for the training of models, but instead this machine learning model learns from the actions. This is the concept where machine learns from the trial and error method, same like we humans learns. Like we take some decisions for the current situation, then we analyze our action, if that action improved the condition or worsened the condition, and based on that feedback, we learn if that action was good or bad for that specific situation. Like how the human learns that how to ride a bicycle. We starts riding, then falls down and learns something, then we try, then falls, now learns more. So with every fall, we learn something new, and by the multiple attempts of bad feedbacks and learnings from them, we learn that how to ride a bicycle. Same way, how we learn to improve our gameplay for any game, we learn from the actions and the feedback. Reinforcement learning works on the same principle. Machine learning model can take any action from the possible actions in the current environment. Then after action, model will analyze the environment again. If that new environment is one step closer to the given specific task, it will be rewarded as a positive feedback. But if the environment goes worse, it will be considered as a bad decision and a negative feedback will be recorded. And by the multiple attempts of actions and feedback, finally a machine learning model will develop. The goal of developing this type of machine learning is to achieve maximum possible rewards so that model can be able to take the decisions in the dynamic environment. Isn't interesting? For me, it's super exciting. Maybe you can relate some of the use cases of reinforcement learnings from the network perspective. If you can think of any new function which you can develop using the reinforcement learning or unsupervised machine learning, let us know from the comment section. Now let's understand what actually a machine learning model is. Let's consider a simple example of supervised machine learning model where we are giving the training dataset as an input where the output is tagged with each and every input. So we are giving the MCS as an input, and based on that we are expecting to have the throughput predictions on some very specific environment. Now, based on the training dataset, machine learning model will develop some kind of knowledge and build the relation that if the MCS is higher, then the throughput is also higher, and if MCS goes down, then the throughput also goes low. This machine learning model will be some mathematical function which can fit this relation of MCS and throughput, and that mathematical function will be used for predicting the throughput for the current MCS value in very specific environment. You can write it like throughput is some function f of MCS. This function f can be any mathematical formula like multiplication with some factors, power with some factor, addition or division of some constant, etc. The job of the training model is to develop that function which fits the relationship of MCS and throughput in any specific environment. Note that we are only considering a single function. However, one machine learning model will have multiple functions and dimensions for good prediction. That is why we are mentioning the very specific environment for our example, because we didn't consider the other dimensions and functions which affects the output, means throughput here. So here is a question for you. Can you name that which type of machine learning model you will use to develop this model for MCS and throughput? Please write in the comment section. Anyway, once you have that machine learning model with the function which has the relation between the MCS and throughput, then simply you can use that model where the system will get the MCS input and the model will predict the throughput. And as in future action, if the throughput not matches or very low in the current network, then you can have the another machine learning model which can predict the possible set of actions to improve that. Or even you can use a machine learning model which can take the action to improve the throughput in the live network based on the different combinations of parameters, radio conditions, user conditions, and many other factors. This way, how the machine learning models works together in the bigger ecosystem. Now let's talk about the basic building blocks in the machine learning development cycle. As we said that the input data is one of the most important ingredient in the machine learning, so the cycle starts from the data collection. If we consider the last example of MCS and throughput, then we will need a lot of good data which can help correlating the relationship between these two parameters. In network system, this data collection can be collected from the network OSS or from the drive test logs, etc., which can cover different aspects. So once you collected all the data, then the next step would be the data preparation. You may hear the general terms like data cleaning and cleansing, etc. So in this step, you filter out the irrelevant data from the collected data, filtering the data which is not complete, or removing the duplicacy in the data, etc. Or maybe you wanted to reformat the data or restructure the data as part of dimension reduction, which can reduce the complexity in the future steps, and you also can correlate the data in a better frame. Now the next step would be the selection of model, which method you should choose for the desired task, what algorithm would be a good fit for the requirement, etc. For the different use cases, you will need different approach, so right selection of model and algorithm is important. Once you finalize that what model or algorithm is a good fit for your specific needs, then you will start training the model by feeding it with the training dataset. For example, if your model is a linear regression model, then the x-axis will be your input and the corresponding y-axis will be your output. So this is important that the linear line is the best fit with the input data points in order to have a good prediction on your user input data. To get this optimal model which can best fit on the training dataset and which will be able to give a good prediction, you will need multiple iterations of training to your model. Now, once you get this good fit model, then you will need to test your model if that model is giving the right prediction on the new data, and for that we generally use the test dataset. This process we call evaluating the model. So you will give the test dataset as an input to the model, then you will get the predicted result which you will compare with the actual output to know the variation in the predicted output and the actual output. If the variation is high and you see the scope of further improvement, then you will go through the more iteration of training the model or tuning the function parameters. And once you're confident that you have a good fit model which is giving the right predictions on the test dataset and the user data as well, then you are ready with the machine learning model which can be incorporated in the real life use cases and can perform the specific task for which it was developed. This model can be used individually for some specific task, or maybe this will act just like a small and individual component of a bigger system. That's how the machine learning systems works. In the last session, we had some idea how the machine learning development cycle works in general. Now, once you have the machine learning model, let's talk about how you will deploy that in the OpenRAN system. In OpenRAN systems, we can deploy different machine learning models at different units for different individual tasks. This generally we segregate depends how these functions or models are sensitive to time. Means if some function need to act fast on the environmental condition, then we will set them up near to the end user. Those models or functions which are not very much time sensitive, those we can deploy at the data centers. This also depends on how big area down the line that function is actually catering. So we classify them in the different control loops in OpenRAN. Let's talk about them. We will start from the loop number 1. You can see that we placed it between the Open Distribution Unit and Open Radio Unit. Means this is near to the UE or user devices, and the interaction between these two units are happening in the real time. So any function which need to act fast on the current environment, that can be deployed at the loop number 1. These tasks are like scheduling management between the ODU and ORU, beam management systems, advanced antenna management systems for resource mapping and signal transformations, etc. In general, those functions who acts per TTI sampling or 1 milliseconds, we deploy them in loop number 1. Now moving to the loop number 2, which you can see integrates between the near real-time rig and OCU. If there is any application or machine learning model which we wanted to deploy in the OpenRAN networks and which need to re-optimize the network in the time frame window of 10 to 500 milliseconds, then those can be deployed in the loop number 2. These applications kind of X apps which can be deployed in the loop 2. So in this loop, the data gets collected and monitored continuously from the OCU and reports to the near real-time rig in the cycles somewhere between 10 milliseconds to 500 milliseconds. And based on the feedback, it optimizes the resources for better user experience and network KPIs. There is one more control loop, which is loop 3, where the machine learning models can be deployed between the near real-time rig and non-real-time rig, and where the feedback can happen for more than 500 millisecond cycle. So you can deploy your machine learning models which are not really time sensitive, for example, kind of RAPs which are being used to optimize the power uses of the RAN systems. Do not worry, we will brief the concept of these apps little later. But if any such application which will not need to optimize within 500 millisecond time window, these can be deployed in loop number 3. like policies management and orchestration management can be happen at control loop number 3. By standardizing these layers of control loops, it will be easy to decide which features and functions and applications can be deployed at what unit in the Open RAN network system so that open resources also can be optimized better. Now let's have some wider picture of how you will deploy your machine learning models in an Open RAN network system at different control loops. So the process starts where the machine learning models gets developed. Designers uses different tools and programming languages like Python, TensorFlow, etc. to develop the machine learning model. So designer will collect the data from the network or other sources and will use that to design a model. Follow up with the tuning and optimizing the model. Once this machine learning model is developed, then it is ready to get deployed in the Open RAN system at the specific control loop like loop number 3 or loop number 2 or loop number 1 for which the model is developed. Now the live data will be collected from down the line units and reported back to the model where the model will take the decisions based on its learning. This new data can also be used for further improving the knowledge of the machine learning model so that it improves continuously for future. Now let's talk about some of the use cases of the machine learning models and its deployment in the Open RAN network systems. So machine learning models not only used for optimizing the network on the current situation, like based on the current feedback and the network conditions, but it can be used for predictive planning of the future network utilization and optimizing the resources to handle those future predictions so that sudden change in the environment will not affect the user experience and network KPIs. Machine learning models can predict the utilization based on the trends and the history, and accordingly it can decide to add up more resources to the specific cell and site from the pool. Or kind of traffic balancing it can also plan between the shared cells and sites. Machine learning model can also be used for automatic network designs. They can predict the ideal locations for future cell or site planning, depends on the coverage gaps or the capacity gaps, etc. In another use case, machine learning models can be used to solve the network problems by their own without direct human interventions. These machine learning models are capable for fine-tuning the parameters in live network and that too in the loop of feedbacks and actions. Means the network will optimize in the current network conditions. Another machine learning model which can be developed using the machine learning is identifying the fraud detection where different kind of rerouting and other techniques gets used to bypass the original services and uses backdoors to get the services from the telcos, which hampers the overall revenue of the telcos. So the machine learning models can identify those users in the network and blocks their bypasses so that the right revenue can come in the stream. Machine learning models can also deploy in solving the customer issues if the reported issues by the customer is generous, like the amount is detected without being using the services or even demand of service. So the machine learning models can take the information from the network history and may take the optimal decision from the telco perspective and customer perspective. So these are some of the most commonly discussed use cases in the market which can be integrated in the Open RAN network systems with the help of machine learning models and intelligent applications. Now let's talk about one example in details. Suppose the requirement is to develop a model for traffic sharing between the cells or sites in the open network based on the resource utilization. This traffic sharing can help improving the user experience as well as the network KPIs. So this is the Open RAN architecture with real-time rake and non-real-time rake. These are connected to the OCU and ODU and serves few cells or sites in some geolocation area. So we considered 3 cells at 3 different sites which are connected to the OCU and ODU in the same pool. There are some users connected with each specific cells and actively using the services like downloading, uploading, voice call, etc. Here, non-real-time rake is collecting the data from the ODU like signal strength, signal quality, radio conditions, resource utilization, number of users, etc. By collecting all these information, radio intelligent controllers knows that some of the cells are overloaded in the terms of resource utilization and number of users, and some of the users which are in good radio conditions with the neighbor cells can be shifted from the overloaded cell to the less loaded cell. If you compare it with the traditional network system, then this performance data is very specific to any cell or site. where individual cell or site gets analyzed for its performance, but with Open RAN system and with virtualization and cloudification of network, where the common resources are shared between the multiple sites and cells in the pool, it has the wider picture in terms of data visualization. Hence, the real-time rake and non-real-time rake are in better position for decision making because it has the data of all the users connected to all these three cells in one pool. So based on these user information and cells performance information, we'll take a decision to allocate the more resources to the overutilized cells so that user requirements in terms of resources can be matched. So it will allocate more resources from the pool to that cell. In this deployment system, you can say that more resources will add for the DU of cell 2 through the real-time rake. So we have E2 interface between the DU unit and near real-time rake. Real-time rake sends this information continuously to the DU for the traffic steering and resource scale up or down. Non-real-time rake and real-time rake are connected with the O1 interface, where non-real-time rake gets the feedback on the control functions and mobility management. Let's talk about one more use case quickly. This is quality of service and quality of experience for the use cases where the bandwidth and latency both are important, such as the example of augmented reality and virtual reality, which requires lots of data transfer for high resolution video streaming and also high latency to get the real-time responses on the actions. So the responsibility of rake is to allocate the sufficient resources to serve the good user experience, and for this, real-time rake required to monitor the performance and the resources requirement continuously, like buffer state, downlink and uplink PRB uses, throughput, latency, radio conditions, etc. And this data can be measured from the different nodes like OCU, ODU and real-time rake. All these information will be feedback to the machine learning model, and based on that, the machine learning model will take the appropriate decision to maintain the right QoE or QoS for the user. In the last few sessions, we talked the basics of machine learning models and their deployment in the Open RAN, so it should be easy to understand the functionalities of rake in the Open RAN. Rake is radio intelligent controllers, and we have two types of rakes, radio intelligent controllers in Open RAN. First is near real-time rake and second is non-real-time rake. Near real-time rake is having the functionalities which are time sensitive, means network should act fast on the decision. Say network should perform the action in between 10 milliseconds to 1 second. Non-real-time rake takes the decision to optimize the network for non-real-time functions which are not time sensitive. So if any function that can wait for more than 1 second for the re-optimization, then that function can be deployed in non-real-time rake controllers. So in simple words, any controlling function which needs to act within 1 second of time frame window, let's deploy them in the near real-time rake, and the other controlling functions which can be performed in more than 1 second, then those can be deployed at non-real-time rake. So you can see in the screen that near real-time rake is closer to the ODU and OCU, and non-real-time rake is placed in some kind of data centers which is far from the users and takes care of non-real-time sensitive controlling functions. Let's quickly map these functions and nodes for the same example of resource management, where the users are connected through the 3 different cells at 3 different locations which are connected to the same pool of OCU, and one of the cell is highly utilized because it has more users actively using the broadband services compared to the other 2 cells. Means it is needed more resources to fulfill the user resource needs. So first, the data will be collected through the NMS. NMS is Network Management System. This collection of data includes what is PRB utilization of the cell, how many number of users attached with the cell, how much data is in the buffer, what is CC utilization, number of users per TTI, etc. These all type of data will be monitored continuously and feedbacks given to the non-real-time rake. Based on this all collected data from all the cells, non-real-time rig will trigger some decisions to release more resources from the pool or size up and size down of the overutilized and underutilized cells, and this decision will be handled by near real-time rig, which will allocate more resources to the OCU and ODU to balance the resources in the respective cells. Now this is one cycle. Again, the feedback will goes to the non-real-time rig based on the new current environment and performance, and this is continuous cycle where controllers takes the decision based on the current network conditions. This was one of the example where you can deploy one functionality at non-real-time rig. Let's talk about the another intelligent function which can be deployed in real-time rig. For real-time rig applications, we need some function which require to act within 1 second of time frame window. So one application is XApps. There are many more applications, but we will talk about this XApps here. So XApps is the concept which uses network slicing to serve more specific type of users. Using this function, network will allocate the resources in the dynamic environment by making a RAN slice. Consider the same network architecture where we have 3 different cells at 3 different locations which are connected to the one OCU in the pool and connected to the same real-time rig with the E2 interface. Now consider there is an enterprise consumer who take in the service which offers guarantee 50 Mbps downlink and uplink throughput for all their employees. This means that rig has the responsibility to provide the sufficient resources to cater minimum 50 Mbps to all of their users. And these users can be connected to any of the cells here. Like some users can connect to cell 1, some connect to cell 2 and some connected to cell 3. But assume that most of the users connected to the cell 2. Note that there will be more users who are connected to the same cell but not belongs to that enterprise unit. So network need to serve those users as well. Okay, so if you understand the requirement, then think about the plan which you can implement in the network. Here, the XApps can help who actually create a network slice. This slice will reserve the sufficient resources for that enterprise user to cater minimum of 50 Mbps to all the users connected to that specific cell or DU. Well, there is one more problem which need to be looked for, because slicing the sufficient resources to cater 50 Mbps to fixed number of users does not mean that all the users will get the 50 Mbps throughput, right? Maybe some of the enterprise users get 75 Mbps and others may only get 25 Mbps. This may also depends on the radio condition of the users. So the users with the good radio condition may have good coding schemes and can get more throughput using advanced antenna techniques like MIMO and special multiplexing or carrier aggregation, etc. So here is the additional responsibility of XApps comes, where it will decide to allocate the required resources through the MAC scheduler in the layer 2 and map the sufficient resources in the physical layer to offer minimum of 50 Mbps to all the connected users. This allocation is required to happen in very short span of time, hence this XApp function has to be deployed in near real-time rig. Now quickly talk about one more application in non-real-time rig. The concept of real-time rig and non-real-time rig was basically introduced in ORAN to develop the more efficient network systems at different stages, which provides more flexibility to deploy the application based on their functionalities. Before talking about this app, you should know that telecom infra is one of the highest investment systems where only RAN part contributes around 70% of capex cost. Also, in the operation of network, RAN parts takes around 60% of overall OPEX cost, which includes nearly 30% cost of energy, means power or electricity, which is required to function of RAN devices, data centers, core networks, etc. This means if we are able to improve the efficiency of this RAN system by deploying some new features and doing some advancement in the existing RAN systems, we can reduce this operation cost in the networks. So RAPS is the feature which is designed to optimize the power efficiency in the Open RAN network system. Let's discuss how it functions. So we know that in 5G and 4G, telcos and operators uses different carriers and spectrum bands to serve their users. Out of these multiple carriers, one from the lower band carrier generally used for coverage and others from the higher spectrum band are being used to add more capacity in the cell or site. To serve these multiple bands, there are multiple radio units gets deployed at the cell or site, and each radio unit required power or electricity to operate as well. This means that more the working radio modules at the site, then more power and electricity is needed at site, means more cost. However, the utilization is not always same. Sometimes cells are needed more capacity when more number of users are demanding the services, and at some other point of time when very less users are connected to the cell or site, then they can be catered with a lesser number of carriers. So this RF senses this requirement and gives the decision that if all the radio units need to be used to serve all the connected users, or they can be handled from the lesser number of carriers. Like when the resource uses is less or active users are less, so in such condition, this RFs will switch off some of the radio units, kind of standby mode or power saving mode, until it senses that now more traffic is coming and more capacity need to be added in the cell. So it will switch on the units accordingly. Now you may already guess that this is something which not need to be decided quickly. Hence, this RFs can be easily deployed in the non-real-time rig, and the benefit is very straight. For the time the radio units are switched off, the power consumption gets reduced. This is one cell or site, and this can be deployed from 100 to 1000 of sites in the network. So the cumulative cost definitely going to be reduced, and that too without hampering the user experience, because they will not get the resource crunch anytime. When they needed more capacity, then it will be provided by switching on those capacity units, and when traffic is less, then the capacity modules will go into the power saving mode. Now we will talk about the cloud platforms for the deployment of Open RAN. In the traditional network system, the resources and the capacity are very specific to the cell or site. The problem with this type of system is that if the cell is underutilized, then the resources in the cell or site will be wasted, and if the traffic on the cell or site is high, then it will require the addition of more capacity and hardware to the specific site, which also needs more time and cost to integrate. However, in Open RAN, we uses Cloudification and uses native cloud systems for the resources, where all the resources are available in the central pool and gets allocated to the cells or site based on their demand and needs. This means based on the present demands, the capacity of the cells and sites will scale up and scale down. By this approach, the resource usage gets more efficient and the wastage of resources gets reduced. And that can happen in the present time condition because the traffic is not consistent throughout the day, like cells and sites in the commercial or office areas carries more traffic in the daytime. However, residential area may take more traffic in the off working hours. In case of any public event, the sites near that event will carry more traffic during the event compared to the other time. So in all such conditions, Cloudification and cloud native networks can automatically reshuffle the resources between the connected cells and sites. These we call O-Cloud platforms, and these O-Cloud platforms can be deployed at different stages of systems, like they can be deployed at the edge or the regional level. The mean of edge level is generally within 20 kilometers from the cell. Means in the edge cloud, central unit and the distribution unit can be placed within the 20 kilometers from the cell area. If you are deploying the O-Cloud within 200 km from the cell or the site area, then this we generally call regional cloud. We put radio intelligent controllers in the regional cloud. Here in the screen, you can see the overview of cloud platform in the Open RAN network system. In the left, you can see the traditional network system for LTE. So here is the radio unit at the site, which is connected to the proprietary BBU baseband unit. They are connected through the conventional front haul called as CPRI. All the layer functionalities of the OSI model from L1 to L3 are being handled by the baseband unit here. Because this is traditional network system, hence the hardware and software functions can only work together. Hence, to move the functionalities to the Open RAN systems, these hardware and software combination needs to be decoupled so that telcos and operators can use the general purpose hardware for computing, processing, storage and networking. These hardware systems in the Open RAN are not proprietary to any vendor or suppliers. Operators just needed some hardware which have general elements for computing, storage and networking, which they can procure from any hardware supplier, and they can put some open operating systems on top of that, like Linux. They can also use the containers in case the cloud native networks is deployed in the network, or alternatively virtual machines can be used. Now the centralized unit and the distribution unit can use the same hardware through the virtualization and hypervisor, and on top of that, orchestrator like Kubernetes can manage those multiple containers or VMs. Now once this virtualization is done and sites is integrated in the cloud, then the units in the traditional RAN system like PPU can be replaced by the ODUs and OCUs, and now RIC will also integrate in the system. As we said that these functions can be placed at the edge location, which is within 20 kilometers from the cell area, or at the regional location, which is under 200 kilometers from the cell area, and all the resources are available in the pool at edge location or regional location, and the capacity of cells will be allocated to them from this pool for their specific need in the current environment. In this session, we will talk about network function virtualization. NFV is being developed by ETSI, which is another big community in the RAN systems. They are working towards virtualizing the different network functions on any hardware. Network function virtualization (NFV) virtually decouples the infrastructure from the different network functions like ODU, OCU, and RIC from the Open RAN perspective. Let's understand it in a simple way. First, we need some general purpose hardware, which includes computation unit for processing that have some storage and that should have the network adapters. In simple, you can consider your computer or laptop which has all these three items assembled. You can deploy the virtualization layer on these hardware through the hypervisor. You can simply understand it like you installed one operating system upon your hardware. Now inside that, you created another virtual machine which reserves some of the resources from your system. Same way with the hypervisor, you reserved some resources from your hardware and created some individual virtual machines which actually sharing the same hardware. So for example, here you created 3 virtual machines, so you can deploy ODU or OCU or RIC on these virtual layers. Like at some point of time, network needs more OCU, then simply system will demand for the additional resource for the OCU and it will be provided from the pool of resources. Then a virtual system will be created and the software function of OCU will be deployed on that virtual machine and it will be ready with the additional OCU unit on the same hardware. So no need to add any additional hardware for the OCU now with the cloud and virtualization system. Same way, we can get any other function whatever is needed in the network. Simply virtualize the resources from the pool of hardware, create a virtual machine and deploy that software function which is needed with the more capacity. This function can be ODU, OCU, RIC or even any individual third-party function. These all the hardware resources and virtual resources are being managed by the NFVM, which is called Network Function Virtualization Manager. The job of this NVM is to manage everything for that NFVI, Network Function Virtualization Infrastructure. Same way, the software instances for the VNF, Virtualized Network Function, are also being managed by NFVM. These management system decides when these VNF systems or NFV systems should on or when these should off, and all these management happens through the orchestration. Means orchestrator is responsible for managing all these different software functions and hardware resources. For example, if any new service or feature is planned to deploy in the network, then from reserving the hardware to managing the software will be managed by the orchestrator. Orchestrator is also responsible for scale up or scale down any function from the network services. Even orchestrator has the power to terminate any service from the system which is not required by the network. So that respective hardware resources can be free and can available for other needy functions. Let's see how it works quickly. So you can see here is the generalized hardware with computation system like CPU and GPU. There is network adapter and some storage devices like NVMe, SSD or HDD or hard disk. Hypervisor is a technique which can reserve some of the hardware resources for some specific virtual system so that one hardware can be shared between multiple functions virtually. This infrastructure is managed by Virtualized Infrastructure Manager, VIM, which will manage these resources to distribute between multiple virtual machines and different functions. These functions can be anything, like in open network, these virtual machines can be used for virtual ODU, virtual OCU, virtual RIC. Also, there are some core network entities which can be integrated in those virtual machines. Like for 5G network systems, we can have virtual AMF, access and mobility function, virtual UPF, user plane function, virtual PCF, policy and control function, etc. These all functions can be enabled or disabled or can be scaled up or scaled down by the VNF, Virtualization Network Functions Managers. Open RAN network systems also has the NFVO, Network Function Virtualization Orchestrator, which manages the VNF and different network functions in the Open RAN. Orchestrator can enable or disable any services from the system as well based on their needs. For example, you need to create the 5G network at some location or wanted to enable some of the 5G services in the network, then it can be managed by the orchestrator. Orchestrator can enable or disable any nodes in the network like AMF, UPF, OCU, RIC, etc. Let's go through the process quickly, how it happens. Suppose OSS, Operations Support System, requests some network function to add in the network. Then this request will go to the orchestrator first, which will validate the request and will check the feasibility for that and will pass the requirement to the VNF, which will check the available resources in the pool and confirms back if the resources are available for the new function. Then orchestrator will give the command to VIM, Virtualization Infrastructure Managers, to allocate the necessary resources for the new function and create a virtual machine or virtual network function. Once the orchestrator gets the confirmation that the virtual machine or the network function is ready, orchestrator will give the command to VNF manager to enable that new function in the network. And that's it. The new network function is ready for action in the network. This was just a high-level overview to understand the cycle, that how it works. You understand that how the orchestrator manages the network functions and how any new network function or network nodes gets created and enabled in the Open RAN system. In this session, we will be talking about software-defined networks and we will know that how these SDNs deploy in the Open RAN systems. Software-defined networking (SDN) is the concept in networking which uses software-based controllers or APIs, application programming interfaces, to communicate with underlying hardware infrastructure and direct traffic on the network. In the traditional network system, we were using dedicated hardwares for networkings like routers and switches for the data traffic on user plane and control plane as well. So you can see the traditional network in the screen where multiple sites are connected together with the switches and routers, and these switches and routers has both control plane and data plane within it. However, in the software-defined network, these user plane and control plane gets disaggregated, and the control plane now placed at one central location for multiple programmable switches, which we call controller machine. Now this controller machine works as a control plane for all the programmable switches, and there is new interface introduced between the control layers and the user data layers. This layer is called Open Flow Interface. In the screen you can see in SDN, software-defined networking, user plane and control planes are separate and they are communicating through the Open Flow Interface. Here the user data traffic is still flowing through the hardware, but the control plane shifted to the software, and that SDN can control multiple data plane network from the central location through the Open Flow Interface. Hence, the configuration gets easy because that can be controlled from one location for all the networks. You do not need to configure individual hardware separately. By using SDNs in the controller, network administrators can easily configure network services and allocate virtual resources from the centralized location. They can control the flow of data between the networks. Also, the shift of data from one network to the another network gets easy, like in case of failure of one network by some reason. SDN will ease the process of adding the security patches in the networking layers, like integration or upgradation of the firewalls, etc. They just need to upgrade them in the controllers through the APIs or applications, and bang, it will be applicable for all the networks down the line. So there are two common SDN. First is OpenSDN, where the network administrator uses the OpenFlow protocols to control the behavior of virtual and physical switches for the data plane nodes. Another is SDN by APIs, where the APIs controls how the data will move through the networks on each physical or virtual switch, instead using of open protocols. This was just a high level of SDN, software defined networking. In this session, we will be talking about multi-access edge computing (MEC), which is an important concept in Open RAN and 5G. Multi-access edge computing (MEC) is the type of network architecture that provides cloud computing capabilities and the IT service environment at the edge of network. The goal of MEC is to reduce the latency and ensure highly efficient network operations and service deliveries and improve the customer experience. This is also called multi-edge computing. So, multi-edge computing or multi-access edge computing framework brings the processing and storage resources for the application closer to the end user, where the services is going to be used. By keeping those compute capacities and devices or resources close to the users, they will be able to get better latency, higher bandwidth, data processing, etc., which offers performance improvement and adds more reliability in the operations of those applications and services. That will also add the security because the data is processing at the edge and not routing through the multiple networks. Like, for example, they can be placed in the hospitals where robots are replicating the actions of doctor in the surgery, which required high precision and latency to operate. Or they can be placed in the factory where machines doing the successive actions in very high sync. Another use case where heavy data transfer and processing is needed, like streaming and monitoring the huge number of video cameras in the security system with the capabilities of AI functions like recognizing the peoples. So these can be placed in the airports, railway stations, etc. So these are some of the use cases where MEC can improve the customer experience and generates revenue from the dedicated stream. Based on the needs, these resources of MEC can be deployed at the client location, like in their factory or workplaces. These are called terminal devices. Another option is they can kept or deploy the devices to the nearest server from the client location. And in the third option, they can be kept at the far servers, like in the data centers or the regional centers. Multi-access edge computing is an evolution in the cloud computing that uses mobility, cloud services, and edge computing to move applications hosts away from the centralized data center to the edge of the network, which is more closer to the end users and provides computing services closest to the application data. Hence, the applications can perform better because the processing task happens more quickly, which can provide ultra-low latency and high bandwidth to the applications along with the radio network information. Hence, radio access networks plays the important role between the end users and the telcos networks because RAN connects the end user to avail any services offered by the telco. This can be voice, data, anything, and also in the MEC implementations too. Let's quickly see that how the MEC mobile edge computing can be deployed in the Open RAN system. So in the screen, you can see there is the user, which is the client area. Another layer is the edge label where MEC resources and applications get deployed. And another section is the cloud backend, which is in the data center or regional center. Any new service that need to be enabled in the network goes to the Open RAN system, which is connected to the MEC host. This MEC host has the hardware and resources for computing, storage, and networking. These resources are reserved virtually for this new MEC platform. Now the steps are almost same, like creating the new function in NFV. The only difference is that now here it manages by the MEC platform managers. So MEC manager manages the MEC application at the edge level. So any new function that need to be deployed in the MEC will be initiated by the OSS and will pass this request to the MEC orchestrator. Now the MEC orchestrator validates this request and will check the feasibility and will ask MEC platform manager to confirm that if it has sufficient hardware resources for the requirement. Once MEC confirms the resources availability to the orchestrator, then orchestrator will give the command to the VIM Virtualized Infrastructure Manager to create the virtual system for this new function, and VIM will confirm it back to the orchestrator that virtual machine is created. Then the orchestrator will communicate this to the MEC manager that everything is ready and MEC can enable the function on it. So that is how it works. In this session, we will be talking about Open RAN deployment scenarios. In the previous session, we learned about the cloudification, virtualization, and the edge computing. Now it's time to understand that how these things can be integrated in the Open RAN systems. But before that, quickly recall some basics of the Open RAN system. So we learned about the different logical functions of Open RAN, which is ODU, Open Distribution Unit, OCU, Open Centralized Unit, and RIC, Radio Intelligent Controller, which can be deployed at different locations, like some can be deployed at the edge location within 20 kilometers range from the cell, and some can be deployed at the regional center or the data centers within 200 kilometer range from the cell site. Which function will deploy where is depends on the type of services, like some services required ultra low latency and some services required high transfer rate and some even required both. Some required edge computing, so we need to configure our network accordingly. We need to define what type of mid-haul we should use. Either we can go with the microwave connectivity or we have to go with the fiber mid-haul. We need to define that what network functions need to be kept near to the users and what can be placed in the data center, like ODU, OCU, near real-time RIC, non-real-time RIC, switch nodes and functions. These all need to be considered before finalizing the ORAN system deployment. Now looks for the Open RAN deployment scenarios. Here in the screen, we have cell site, then we have the edge cloud area, which is within the 20 km radius from the cell site, and we have the regional cloud or data center, which is within 200 km radius from the cell site. So consider the scenario A, where virtual ODU, virtual OCU, and near real-time RIC are deployed at the edge cloud area. ORU obviously will be at the cell site. This scenario can be deployed to provide the low latency kind of services because OCU is placed at the edge cloud and also good for the broadband services. Now, second option is option B. In this case, ODU and OCU is still placed at the edge cloud but near real-time RIC now deployed at the regional cloud. This can be implemented in the dense areas. Latency will still low as OCU is still near to the cell or site area. Next option is option C, where the ODU placed at the edge cloud but OCU and RIC are deployed at the regional cloud. Here we have one more similar option with little tweak. So this is called option C1. Here centralized unit divided into two parts. One is for control plane and another is for data plane. So the user plane kept at the edge cloud so that latency can be kept low for the services, and the control plane functionalities kept at the regional cloud. If you wonder that what are these 1:64 and 1:100 mentioned in the screen, then it means that 64 ODU units can be catered by one OCU simultaneously. This is as per ORAN Alliance's specifications. Same for 1:100, 100 ODU units possible over one OCU. Note that this also depends on the available hardware resources as well. So C1 is the more advanced option to consider. Next is option D, where the ODU is physical hardware, not the virtual unit. Unlike the other options we discussed yet, this is again for the outdoor deployment. So ODU is placed at the edge cloud. Virtual OCU and RIC are placed at the regional cloud. There are two more options, which is option E and option F. Option E targeted for the indoor scenarios and option F targeted for the outdoor scenarios. Out of all these options, option C1 is widely applicable for most of the deployments. Others are very specific to the services and applications. This was the quick overview of the ORAN deployment. In Open RAN, we disaggregated some of the functionalities and components. So it is very important that these all components must have good connectivity between them for operations. In this session, we will talk about the front haul connectivity, which is enhanced CPRI or eCPRI, which is the new protocol and enhanced version of 4G CPRI. We will also explore the option of mid-haul connectivity other than the fiber line, like microwave connectivity, which is not a top-notch solution, but yes, we have the option for the mid-haul. We will understand the connectivity between the RUs, radio units, and DUs, distribution units, as well as between the DUs and CUs. So first, we will go through with the traditional transport network system, which was used in 3G and 4G networks. The connectivity between the radio access network and the core network is called the backhaul in the traditional network system. which is generally provided by the fiber line connectivity or microwave connectivity. But in the Open RAN system, baseband unit functions are now separated in the ODU, Open Distribution Unit, and OCU, Open Centralized Unit. Hence, we need the proper communication between these units in order to make them work together. Hence, the concept of mid-haul comes, which provides the connectivity between the centralized unit and the distribution unit. And we also have the front haul, which provides the connectivity between the distribution unit and radio unit. Now the problem is, earlier the front haul has the lower capacity like 1 to 10 Gbps, but as the technology gets advanced, we required more capacity in the front haul as well. At present, it is 10 to 50 Gbps expected. This means the overall capacity needs to be increased from back haul to mid haul to front haul. But for the front haul and mid haul, we also needs to take care of the latency, which is expected to within 0.1 millisecond in the front haul. So the Open Cell Form community came up with the evolved protocol named as eCPRI for the Open RAN and 5G. However, there is another challenge because ODU and OCU are separated and placed at the different location. So how this level of latency can be achieved if they are placed at the long distance? Here in the screen, you can see old CPRI and the evolved CPRI side by side. CPRI is Common Public Radio Interface. In the old CPRI, which is being used in 4G and which can offer nearly 300 Mbps with 20 MHz bandwidth together with the advanced antenna techniques like MIMO. So that transfer rate is far low from the CPRI capacity, which was designed to offer up to 12 Gbps. However, this also depends on the number of cells connected to the 1 BB unit, but still the number of conversions of frequency to time or time to frequency domain is less from the CPRI capacity. But with the 5G technology, the end-to-end throughput is expected to reach about 20 Gbps, and with more technology enhancement, it may go beyond. And hence, we need to increase the capacity end-to-end. This means front haul also need to be evolved. So instead BBU, in Open RAN, RU is connected to the ODU and the requirement of front haul is now changed to support up to 100 Gbps. Hence, to fulfill this heavy requirement, a small cell form comes with a new protocol. This is eCPRI protocol, which have the capability to achieve the high number of fast Fourier transforms and inverse fast Fourier transforms through eCPRI. Now let's talk about the mid-haul, which has the connectivity between the centralized unit and distribution unit. The requirement of heavy transfer rate is also applicable here. So the best way is to use the fiber connectivity as a mid-haul. But as an alternative, microwave option is also there from very high frequency range, like ranging from 60 to 90 GHz band like E-band, which can provide the wireless mid-haul between the CU and DU. However, the lower frequency bands which are being used earlier like 18 to 14 GHz or narrow band frequencies like 6 to 15 GHz bands, we cannot provide the new required capacity from those bands. But there is a trade-off in using the higher frequency bands. That higher frequency bands can provide the capacity but cannot serve the long distances. However, the narrow frequency bands can serve the longer distance but they cannot provide the same capacity as E-band. Theoretically, E-bands can offer up to 10 Gbps connectivity in the mid-haul, compared to the narrowband microwaves, which has just 2 Gbps capacity to serve. There is one more downside of the microwave connectivity, and that is availability, which is lower than the fiber connectivity. We will be talking about that how the 5G can be integrated in the Open RAN ecosystem and how the Open RAN can be placed as the base ecosystem and infrastructure. We will discuss that how the different RAN functions units and the core function units can be virtualized and a step ahead in the cloud native ecosystem. So we will be focusing on end-to-end network architecture with the prime focus on 5G standalone deployment architecture with the 5G core network. We talked a lot on the RAN functions and its components. Now let's have some overview of the core network units and their functions. So we have two types of architectures in the 5G deployment. First is 5G NSA, which is 5G non-standalone, where the RAN network is 5G, but core network is still shared with the legacy networks like 4G. Another is 5G SA, 5G standalone, where the RAN network and the core network architecture belongs to 5G only. Telcos with the existing 4G network, they deploy the 5G NSA first and slowly upgrade to the 5G SA. The common core network functions: number 1, establishing the secured connection among all the connected devices. Number 2, applying the policies and charging the users for availing the telco services is the job of core network. Number 3, core networks handles the session management and the mobility management. Like we talked how the AMF handles the mobility in the RRC connected mode. This is part of core network. Number 4, core networks do the routing and rerouting of the user data, like how the data reaches to the end user. Number 5, core network also maintains the QoS of the services, like which service need to be handled first, which has higher priority, etc. Let's quickly see the 4G core network elements and 5G core network elements side by side. In 4G, we have MME, Mobility Management Entity, which manages the session management functionalities and mobility management functionalities. But in 5G, the responsibilities are disaggregated to maintain the QoS better, and the user plane and the control planes also get separated. That allows some of the new functionalities in the 5G network like slicing. Let's focus on the 5G standalone architecture. We will talk about control plane first and then the user plane, as they get separated in 5G. Suppose your mobile wanted to connect to the 5G network, then it need to be connected to the AMF first, which is access and mobility management function. AMF will authenticate the user before providing them access to the core network. AMF do this with AUSF, authentication server function. AUSF will coordinate with the UDM. UDM is Unified Data Management, which has all the data about the user subscriptions, like either user has the calling services or the data services or roaming services, etc. So UDM confirms to AUSF that yes, this particular user can avail the service which is demanded. Then AUSF notifies the same to the AMF. So this is the initial access authentication. Another function of AMF is mobility management, like when the user moves from one cell area to the another cell area, AMF takes care of the mobility actions. Another component is PCF, policy control function. This unit is responsible for charging the user for the availed services. Another component is SMF, which is session management function. This takes care of all the sessions and the protocol data units which are flowing between the users and the core network. Initial IP allocation to the UE also managed by the SMF. The flow of PDU sessions from the core network to the user and user to the core network will be managed by the SMF also. Now coming to the user plane functionality, it is handled by the UPF, which is user plane function. This is straight. Any user data that is flowing from user device to the core network or from the core network to the user device goes through the UPF. This takes care how the packets will be routed and forwarded from core network to the user device. This UPF connects to the external network like internet, and the data flows from internet to the user device and vice versa. This will be quick and small recap of basic terminologies of Open RAN ecosystem and quick recap of ORAN deployment architecture. We will start from the quick architecture overview. You can see that there are different nodes and functions located at different places and interconnected with some interface. We have the general purpose hardware setups which are shared between the different functions through the virtual machines and virtual functions. We have virtualized infrastructure managers, VIM, to manage the VNFS, virtualized network functions. The architecture in the screen of ORAN and 5G technology gets deployed on top of it. And we have different deployment options as well, which can be used to cater different type of services. And based on the needs, we can place these network functions at different locations. Like some functions can be deployed at edge level and some can be deployed at regional level. And even some can be deployed at customer locations too. Same way, you can see the 5G core network functions. In some cases, they are placed near to users like at edge cloud if the services or applications needs low latency, and for some other use cases, these can be deployed at regional cloud. Some other control plane functions are generally kept at core cloud or in data centers like virtual AMF, access and mobility management function, virtual UDM, unified data management function, virtual AUSF, authentication server function, virtual PCF, policy control function, and SMF, session management function. You can see that virtual UPF can also deploy it at core cloud in some cases. Now you can feel that deployment of functions are how convenient in Open RAN systems, and they also provide the great level of flexibilities. Next, you can see the operational applications which can be deployed in the network at different stages. These can be third-party applications or APIs who can offer very specific use case to the telcos. And these can be based on AI, artificial intelligence, and machine learning for new and more advanced features. To control all these functions and enabling them, disabling them, terminating them, starting them, etc., we have orchestrator on top of that, who coordinates with all the managers and sends the instruction to fulfill the network requirements based on the needs and for continuously optimizing the network resources. Let's quickly recall what function do what action in very brief. AMF in 5G, access and mobility management function. This is control plane function in 5G network. AMF is responsible for registration and deregistration of users with 5G network. It handles the establishment and release of signaling. AMF is also responsible for tracking the mobility of the UE locations. UDM, Unified Data Management. This is again part of core network and handle control plane functions. This is same like HSS in 4G, but the HSS responsibility is split in 5G between UDM and AUSF. So UDM manages the user data like data of subscribers and their subscriptions. AUSF, authentication server function, has the responsibility to authenticate the user if he is applicable to access the network and availing any service. It also communicates with the UDM to get the subscriber data. It is also the control plane function and part of core network. SMF, session management function, again function of control plane and part of core network. SMF is responsible for the PDU session management. ODU, open distribution unit. OD unit is responsible for higher physical layer, MAC layer function and RLC layer functions in the RAN protocol stack. These layers works on NFV, network function virtualization, or containers in case of cloud system. The COD server, commercial of the self, first installed with the NFVI software, which enable the virtual resources like compute, storage and network. ODU software or application then gets installed on this virtual server and your ODU is ready for function. There is orchestration software on top of it which manages all the underlying softwares and hardwares for upgrades, scale up or scale down or the hailing purposes. Next is OCU, Open Centralized Unit. OCU handles the higher physical layer functions of BBU. OCU handles the PDCP layer function and SDAP layer functions. It also handles the RRC function for the control plane. Radio Intelligent Controllers. RIC is responsible for all the RAN operations and optimization procedures like RRC management, mobility management, QoS management, edge services, etc. Third-party application which can be based on AI, artificial intelligence and machine learning can be set up on RIC for best network optimization and can provide the good user experience and provide the effective network operations. In the Open RAN architecture, RIC is further classified into near real-time RIC and non-real-time RIC. Near real-time RIC controllers connects to the CU and DU units through the A2 interface and it connects with the non-real-time RIC through the A1 interface. Near real-time RIC can control the mobility management, QoS management, interference management, radio connection management, etc. This was the high-level overview of Open RAN ecosystem. I hope now you are aware of the terminologies which are generally used in Open RAN system. We will gradually increase the insights for different Open RAN functions in the later series. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video and don't forget to share. Thank you for watching.